Hey my Wholemood students, how you guys doing? Hope you guys are good and well and fine and ready to do some science. So this is actually our first tutorial, lectural, teacher video, and I hope you guys are ready because I know I am. Before I get into this video, I would like you to please hit that subscribe button, hit that share, hit that comment, and tell me what you think about this video. And by the way, I'm a first year student at the University of Western Cape, and we are going to be doing the chemistry of life today with a very big emphasis on bonding and atoms and the whole theory around it. A whole entire mood. So the vlogation. So before we get started, we're going to define some terms, then we're going to dive deep into the concepts. Are you ready? Because I know I am. Let's get it. Okay, so before we get into it, the first thing that we are going to do is define matter. So matter is anything in the universe that takes up space and has mass. So pretty much everything on planet Earth, in Jupiter, and everywhere else around the universe is made up of matter. So now we have matter. Right? Matter, like I said, matter is anything that occupies space and has mass. So everything else pretty much in the universe is made up of matter. And matter is broken down into elements. So an element is a pure substance that cannot be broken down further. So now when we go onto our periodic table, we find the periodic table of elements, and then we have about 118 elements, and each and every element has its own properties that makes it different from other elements. But when we come to our periodic table, we can see, I need you guys to come to pause this video and get your own periodic table, because now my periodic table is probably too small to be seen through the camera, but I can see it. Now, when we come to the periodic table of elements, we can see that from on top, it is written 1A, 2A, 3A, 4A. So basically, what that means is that elements in a periodic table are not really separated, but are distinguished into different groups, and the vertical rows are called groups, and those groups arranges elements in terms of the same chemical properties. So as you can see, number one is hydrogen, then the element behind hydrogen is lithium, then it's sodium, then it's potassium. All the elements in group 1A have the same chemical properties. Then when you jump down to the next one, where we have beryllium, magnesium, calcium, going down, all those elements have the same chemical properties. And then we come down to 3A, where we find boron, aluminium, and then going down that row, we find elements with the same chemical properties, and so on and so on and so on. And then when you see now, if your periodic table is going to have number 1, 2, 3, 4, 5, those numbers separate them into groups, and then those groups all have so all elements in sorry, not groups, periods. All elements in period 1 have the same number of electron shells. So now, since it's group 1, it means that it has 1 electron shell, and then period 1, and then period 2 elements have 2 electron shells. Period 3 elements have 3 electron shells. And then we will get back into that later on in the video though. I was just trying to explain the whole concept of element. And then elements are made up of atoms, right? Well, no, actually, elements make up atoms. And then atoms, it's pretty much groups of elements that have the same characteristics and and have properties of that particular element. So now we have hydrogen. You can have hydrogen as a, oh, the dogs outside are barking. I'm really sorry about that. We can have hydrogen as a monatomic element. Well, monatomic atom, which means that there is only one hydrogen. Then I'm so sorry for your barking dogs. So then now atoms, we can have monatomic atoms whereby it's just one atom. Then we have diatomic atoms where it is two atoms of the same elements. Like, so now we can have H, this is monatomic. Then if we have H2, that is diatomic. So now that is two atoms of the same element. Two atoms of the same element. But then now when we have H2O, we have three atoms composed of two elements. You see, we have two atoms of hydrogen, which is the same element, and one atom of oxygen, which is a different element, meaning that we have three total atoms composed of two elements. Now you see the difference between element and atom. And then each and every atom is made up of protons, electrons, and neutrons. So protons are found within the nucleus of an atom and have a positive electrical charge, right? Positive electrical charge. So they are positive. And then electrons, they form a cloud around the atom and they have a negative electric charge. And then neutrons, they are also found in the nucleus of an atom and have no electrical charge. So they are electrically neutral. So protons and neutrons, they are found within the nucleus, inside the nucleus of an atom. So basically, if this is an atom, this is going to be a nucleus, and then around we are going to have clouds, and in these clouds are the electrons. An atom is made up of a very, very tiny nucleus that contains most of the mass of the atom, and the nucleus is composed of protons and neutrons. And then the other part is of an atom is an electron cloud, which covers most, literally over 95, over even 99% of the volume of the whole atom. And it is composed of electrons, which are essentially weightless, right? And then when you put your protons, so protons alone, they make up the atomic number, which is the number that you see on top of each and every element. And then the atomic number is the number of protons. And then when you put together the number when you put together electrons and protons, you get the mass number. Yes, the mass number. So the mass number is composed of the protons and the neutrons. And then the atomic number is the same as the number of protons, right? So for hydrogen, which is number 1, has 1 proton, it has an atomic number of 1. And then for lithium, it is 2. And then for helium it is 2, for lithium it is 3, for beryllium it is 3, it is 4, and so on to the next one and next one and next one. Isotopes are elements with let's just say atoms with the same number of protons but different number of neutrons, meaning that they have different mass numbers. And the most common isotope is carbon. The most commonly used isotopes are the carbon isotopes, which are the isotopes that I will use for this demonstration in an example. So now we have carbon 12, carbon 13, and carbon 14, right? So now if you come to your periodic table, you'll find out that carbon is number 6, right? It is number 6 on the periodic table, which means that it has 6 number of protons. So now you will have your 6 here at the bottom, your 6 here at the bottom. So now this is how you represent atoms. So now the number at the bottom represents the number of protons. Then the number on top shows us the mass number, and then the C just tells us that it is carbon. So now, since we see that we have 6, 6, and 6, it means that it has the same number of protons. So they all have 6 protons, right? But then carbon 13, well, carbon 12 has 6. So carbon 12 has 6 neutrons. And then carbon 13 has 7 neutrons, and carbon 14 has 8 neutrons. So now to find these differences, you take the big number, which is the mass number, and then you subtract it from the small number, which is the atomic number. In each and every single element elements have carbon, come rain, come thunder, it will always have 6 protons, but it can have different number of neutrons, which will lead from hydrogen to the last known element. They can have isotopes, right? We have the abundant isotope and the non-abundant isotope. The abundant isotope is the isotope that is found the most in nature, right? And in this case, it is carbon 12. And then carbon 13 and carbon 14 are not really found that much in nature. And then when you look at your periodic table, you will see a number, and a number at the bottom of the type of elements. For example, in carbon, we see that the number is 12,0,107. You see this number here, this is your average atomic weight. Your average atomic weight. And then the average, well, it's actually usually called the atomic weight, and the atomic weight is the average of all the isotopes. The average of all the isotopes. The average of all the isotopes. And this number will always be greatest or closest to the isotope that is most abundant in nature. In the case of carbon, you can see that this number is 12,0107, which is really close to carbon 12. So this tells us that carbon 12 is the most abundant isotope, right? It makes up most of the carbon that we find in nature. We get it now. Good. So then now that we know about atoms, now that we have knowledge about atoms and how atoms are made and their properties, now we will go into chemical oh my goodness. Now, oh my goodness. Oh no, that does not look nice. Now that's better. We are gonna go into chemical bonding. Chemical bonding. So a chemical bond is a bond that holds atom. So it's actually in attraction that holds atoms together. It's just that attraction that holds atoms together. So now we are gonna first describe what a molecule and a compound is. A molecule is a substance that is made of 2 or more atoms, and then a compound is a substance that is made of 2 or more different elements. You get it? So A molecule is usually made of the same elements, but then an atom is made out of, a compound is made out of different elements. In the case of H2, H2 is a molecule because it is the same element of atom hydrogen. Then H2O, it is different elements, so now it makes it a compound. Get it? Get. So now we are gonna go into, we are gonna describe what an orbital is. An orbital is, okay, let me write it down. So we just, okay, let me put it down to save space. We just describe what a molecule is and what a compound is, right? And then now we just describe what an orbital is. Okay, so an orbital is the most likely location of an electron, right? We say the most likely location of an electron because electrons are in constant motion every single minute, second, hour. So there is no way you can know the exact location of an element. So that is of an electron. That is why we use the term orbital, and we say the most likely location, right? And then now an orbital can hold a maximum of 2 electrons, and then within an orbital we have an electron shell, and then an electron shell is a shell that holds orbitals of the same energy level. So now the smallest shell can hold 1 orbital and 2 electrons, and then a bigger shell can hold 4 orbitals and a total of 8 electrons, which means that 1 orbital can hold a maximum of 2 electrons, and then the biggest electron shell can hold 4 orbitals and a whopping total of 8 electrons. Now that's some numbers, okay? And then we have the inner shell, which is the innermost energy shell that is closest to the nucleus. And then we have the valence shell, which is the one that we're interested in, which is the outermost occupied electron shell of an atom, right? Yeah. So like I said, now we okay, like I said that the periods, the period number tells us the number of electron shells. So now if the period number is 1, we have 1 electron shell. If the period number is 5, we have 5 electron shells. And then within the groups, we have group 1 to group 8. Now now I'm talking about the main group elements, the ones with A's, the main, not the transitional elements, not the ones with B's that are found here. No, the ones with A's, from hydrogen, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Those are the ones that we're talking about. The ones with A's, the main group elements. Those ones tell us the number of valence electrons in the most occupied electron shell. So hydrogen has 1, beryllium has 2, carbon has 4, neon has 8. And then the electrons in the last group, you can see them, the ones with 8. Those ones are noble gases. They are usually called noble gases, like they are noble because they are chemically unreactive, and they're like the kings and the queens of the world because they are found in nature without combining with other elements. Maybe they are found by themselves. They're just like, you know what? I'm the king, I'm the one. I don't need to connect with anybody. I'll connect with myself. Like they have so much pride to the point where they're like, no, they don't form chemical bonds. No, they do not do that. So they are called noble gases. And then the first two groups are called metals. And then if you can see in your periodic table, before boron starts, there's like a zigzag line. Elements on that zigzag line are called semi-metals or metalloids, and then elements after that line are called non-metals. Right? This is very important in chemical bonding. Okay, so now we have ionic bonding, and we have ionic bonding, covalent bonding, and hydrogen bonding, and those are the bondings that we are gonna be focusing on in this video. So for starters, we have ionic. So ionic bonding is when an electron, right, that is very, so now let me explain electronegativity. Electronegativity is the tendency of an atom to attract electrons to itself, So now in ionic bonding, this is the bonding that is found between a metal and a non-metal. When you see a metal and a non-metal coming together, just be like, yes, it is ionic bonding. And the non-metal is, so in ionic bonding, one atom literally steals an electron. It takes completely an electron from a different atom, and usually that atom or element is usually a non-metal because it is more electronegative. And electronegativity has a scale of 0 to 4, with 0 is like not electronegative, and 4 is like yes, very electronegative. So non-metals are very, very, very not electronegative. But non-metals on the other hand are very electronegative, with fluorine being the most electronegative element we have in the periodic table. Like literally, like it is very, very electronegative. And then now, when ionic bonding, usually between ions, whereby one ion has a positive charge and the other one has a negative charge, and then they come together and then they steal the atom of the other one. But then now we are going to make an example with sodium and chloride, and how chlorine steals an atom from sodium, and then sodium loses, and it doesn't steal an atom, it steals an electron, and then sodium loses an electron, and then it becomes positive. Well, it gains a net positive charge, while on the other hand, chlorine gains a net negative charge. So now we have sodium and we have chlorine, right? So now we are gonna come to our periodic table and look at chlorine. So now we want to put all the electron shells and the orbitals, right? So since sodium is number 11, the first thing that we are gonna do is make our first. So this is our first electron shell, which has 1, 2, how many? 2 electrons and 1 orbital, because it is the innermost one, right? Then the next one holds up to 8 electrons. So now we're gonna have 3, 4, 5, 6, 7, 8, 9, 10. We still have 1 more electron left. So now we put in another one. Then this is 11. And we're like, yeah, we did the things, right? And then, like I said, the group number tells you the number of valence electrons, the number of valence electrons. So now the number of valence electrons in the valence shell. And now since sodium is in group 1, it means that it has 1 electron in the valence shell. And then now we go down to chlorine, which is number 17, right? Is it number 17? It is number 17. So now we are going to have the first round with 1, 2, then we're going to have the second round with 3, 4, 5, 6, 7, 8, 9, 10. Then we're going to have the third round with 10, 11, 12, 13, 14, 15, 16, 17. Right? 17. Then we have a plus, meaning that they come together, and then you see now, for chlorine, and atoms are most stable when their valence shells are full, meaning that they have 8 electrons around the valence electron shell. So now sodium has 1 electron in the valence shell. So now it doesn't need it. It literally doesn't need it. And then chlorine has 7 electrons in the valence shell, and it needs 1 more electron for it to be stable. So this one is transferred to over here. Is transferred to over here, right? And then the overall bonding that we are going to have Na, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See, now it has 10 electrons instead of 11 because it donated this one, and now it bears a positive charge. It bears a positive charge because it lost 1 electron, right? And remember, electrons are negative. So now since it loses 1 electron, it becomes more positive because it lost a negative situation, right? And then now this is now an ion, and then an ion is usually the same as the preceding noble gas. In this case, sodium now has the same structure as neon, which is the preceding noble gas. Now sodium itself is noble and is like yes, but then now this is not done. And then now for chlorine, now we can have chlorine, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? Then this is now negative. The reason why it is negative, it is because it got an electron from sodium, and remember that an electron is negative, so now it is more negative, right? You get it? And now this is a chlorine ion, and then negative ion have the same chemical structure as the noble gas after it. So in the case of chlorine, the noble gas is going to be argon. So now it looks exactly like argon. So all the elements in group 1 form ionic bonds with all the elements in group 7. Then the elements in group 2 form ionic bonds with elements in group 6. Yeah. And then now covalent bonding, it is the sharing of electrons. The sharing of electrons between 2 or more atoms. And then remember, ionic bonding, it is when one element steals an atom from another element, then we bear a positive and a negative charge. And then now covalent bonding, it is the sharing of electrons. And yeah, now we have, let me just show you one example. Let us use oxygen. Let us use one single bonds first, then we're gonna go to a double bonded one. One with single bonds will be, let us use methane. Methane, where we have carbon, which is number 4, which means that it has 4 electrons in its valence shell. So now this is literally a very simplified form of this, whereby I am only listing the electrons in the valence shell, not the electrons in the inner shell. Now you can use either way, it's the same, as long as you know how to do the math, then you are good. You know what I mean? And then now for carbon, it has 4 valence electrons, so it's 1, 2, 3, 4. And then remember, methane is CH4, right? CH4. Then it's going to bond with 4 molecules of hydrogen, right? It's going to bond with 4 molecules of hydrogen, right? And then now you see that hydrogen only has 1 proton, one electron. And now for carbon to be stable, it needs 4 more electrons so that it can have 8 electrons around it. So now since 4 molecules of hydrogen make methane, this is going to be a total, well, an overall structure of those saying. So now the total structure is going to look like this, whereby these arrows represent a single bond, a bond. So now you can represent this, not arrows, these lines, you can represent it as dots or as lines. It's the same thing, dots or as lines. But then now you can see that the difference between covalent bonding and ionic bonding is that in ionic bonding, one electron is stolen, and then in covalent bonding, electrons are shared equally, not really equally, but then they are shared between the 2 elements or more, 2 or more elements that are bonding. And then sometimes we have double bonds or triple bonds, whereby there are 2 pairs of electrons being shared between the 2 electrons in the situation. So now a classical example for double bond is oxygen, whereby we have 2 molecules of oxygen doing this. We know that in its valence shell, oxygen has 6 electrons, right? So now it's going to do this 1, 1, then we're going to have that. So as you know, this is a classical case of a double bond. In a triple bond, it is 3 pairs of electrons being shared between 2 molecules, between 2 atoms. Then in the case of nitrogen, whereby we have 1, 2, 3, 1, 1, 1, 1, we have a triple bond. And then obviously a single bond is longer than a double bond, and which is also longer than a triple bond. And obviously now, since a single bond is going to be weaker than a double bond, which is going to be weaker than a triple bond, so a triple bond is very strong. It's like trying to break these 3 cookies at the same time. It's just going to take a lot of energy, but trying to break 1 cookie is going to take much less energy, right? And then we have polar bonding, and write it down. We have polar bonding, well, polar covalent bonding and non-polar covalent bonding. And this is where electronegativity also plays a part. So in polar covalent bonding, we have electronegativity that is not really great, but it's moderate. It's moderate to high, and that is usually found between when 2 nonmetals of different elements are bonded together. When 2 nonmetals of different elements are bonded together, we get a polar covalent bond. And a classical case is the bonding of water, of 2 hydrogens and 1 oxygen. And then the electronegativity is usually between 0.4 to 1.7. So the difference is usually between, let's use a different pen so you can see properly. It's usually between 0.4 to 1,7. And then a non-polar covalent bond, it is a bond whereby it's elements usually of the same elements, whereby the electronegativity is the same and they bond equally, right? In polar bonding, since the electronegativity is different, electrons tend to surround the nucleus of the more electronegative molecule than the other molecule. And then in nonpolar bonding, since the electronegativity is usually the same, the bonding is shared equally, the electrons are shared equally, and it is in the case of O2 and N2 bonding together, and it is usually elements of the same atom, right? And it is usually diatomic elements. And then yeah, the electronegativity difference for here, it is very, very small. It is usually between, it's literally smaller than 0.4. And then the electronegativity for this, it is very, very big, because it is between a metal and a non-metal. So the electronegativity is very huge, and it is usually greater than 1 to 1,7, right? And then yeah, and then now another special type of bonding is called, excuse my mouth, it is called hydrogen bonding. Hydrogen bonding is the bonding that is found between well, when two atoms with opposite partial charges are bonded up, and you see. So yeah, it is an extreme special case of polar bonding. Yeah, and then it gives us in hydrogen bonding. And the reason why we call it hydrogen bonding, it is because it is usually between hydrogen and a different element, and hydrogen is the element that is, whenever we have hydrogen bonding, hydrogen is always the element that takes the partial positive charge, then the other element takes the partial negative charge, and then they exert forces of attraction to each other. And then the electronegativity difference there is literally the same as for polar bonding, right? And then now that one is called hydrogen bonds. What is it? What's up? So yeah, so now for a quick recap, ionic bonding, it is when one element steals an atom and steals an electron from another element, and is usually between a metal and a non-metal. The electronegativity difference is very huge. It is usually greater than 1.7. And then we go to polar bonding, whereby let's say covalent bonding, whereby electrons share atoms. And then we have polar covalent bonding, whereby one element attracts and pulls electrons and has the electrons around the nucleus more than the other one, bearing a positive and a negative charge between the two elements. And the electronegativity difference is usually between 0.4 and 1.7. It is moderate. It is always smaller than the one for ionic bonding. And then non-polar bonding, it is between the sharing of electrons between two elements that have the same or almost the same electronegativity, whereby the electronegativity is usually less than 0.4. And then we have hydrogen bond, which is a very special case of polar bonding, and it usually occurs when there is a hydrogen, and we call it hydrogen bonding because hydrogen is usually the element that takes the partial positive charge, right? And then there it is. There you go. Literally, we covered a very big topic today, and thank you very much for being consistent. Thank you very much for watching this video. Thank you very much. I just hope that I taught you something, you caught something, and you learned something from this video. And remember, for you to pass science, you gotta practice, and practice. That is the only way you can do it. And thank you very much for watching this video. I'll be posting more science related videos from now on, so be sure to tune in, be sure to subscribe, and be sure to share the video. Thank you very much for watching. I really appreciate it, and I hope you got something from this video. Thank you. Mwah.